Coriolis flow meter is very expensive, okay? Very expensive. For example, if you have 1 meter per second in 2-inch pipe, so 1 meter per second is a rough number for most of the time when you have flow in the pipe, it's about 1 meter per second. It's not more than 10, okay? Most of the time it's about 1 meter per second. If you have 1 meter per second in 2-inch pipe, your flow meter can be, if you use Coriolis flow meter, it can be somewhere between 10,000 to 10,500 to 15,000. So it's expensive, okay? So now you know the working principle of the Coriolis flow meter. In the exam or in the quiz, I will ask about working principle of Coriolis flow meter. How does it work? And you need to know that, okay? Okay, next one. Turbine meter. Just take a look at the meter.
A rotor. The rotor is constructed of titanium, which was chosen for its lightweight, high tensile strength, and excellent corrosion resistance. The flow stream, depicted by the flowing blue arrows, is channeled by the upstream stator through the rotor. The rotor, like conventional turbines, rotates on a fixed shaft with a virtually frictionless, highly polished tungsten carbide bearing system. The rotational speed of the rotor is directly proportional to the axial flow velocity of the fluid. The fixed shaft tungsten carbide bearing design is the same as the bearing systems used in the Century Series turbines for over 40 years in harsh crude oil service. A high-strength permanent magnet is embedded in the tip of each blade of the rotor. As in conventional turbine meters, a pickup coil is located directly above the rotor and is completely isolated from the fluid. It is constructed of many coils of fine wire that are wound around a core of paramagnetic material. As each blade passes underneath the pickup coil, the passing magnetic field induces an AC voltage in the coil, which is seen as a sinusoidal wave.
So basically you have a blade in the middle that keeps spinning, right? The blade keeps spinning and you count how many times that you spin or how fast you spin and then convert that back to the flow rate, okay? This is turbine meter. So it's one type of kind of positive displacement for the turbine meter. That's okay. This one is for lag unit, so you need to
In
watch
this
this.
animation, we see a Smith meter rotary vane PD meter in operation. As the transmitter, calibrator housing, and cover with transfer gears are removed, we see the heart of the meter, the rotary vane design. The fluid flow enters the meter on the left side. The block at the bottom of the meter separates the inlet from the outlet and prevents the fluid from bypassing the measuring chamber. Instead, it is channeled around the rotor into the measurement section. The fluid is continually separated into discrete segments in the measurement section.
So the previous one is not really true positive displacement, right? Because there can be some liquid channel through. But this one is really positive displacement. You actually count how many volume go from left to right, okay? And this one is used in the lag unit. Which one is this? Oh, okay. This one is...
Gaudet. On the differential pressure principle. Some 300 years ago, Swiss mathematician and physicist Daniel Bernoulli discovered the direct relationship between the pressure and speed of a fluid flowing in a pipe.
So if I show this picture, will you be able to tell who's him? Okay, let's not have that in the exam. This is Bernoulli, okay?
Italian physicist Giovanni Battista Venturi also performed experiments on flow, and in 1797 he built the first flow meter for closed pipes, known as the Venturi tube. Here is how this measurement method works. Differential pressure flow meters have an artificial restriction integrated into the measuring tube, illustrated here by the example of an orifice plate. Two holes are located in the pipe wall, one before and one after the orifice plate. Two separate tubes connect these holes to a differential pressure sensor with its two pressure chambers separated by a diaphragm. The tiniest pressure differences in the flowing fluid can be precisely measured. If the fluid is not flowing, the pressure before and after the orifice plate is essentially identical. As soon as the fluid starts to flow, its velocity around the orifice plate increases significantly because of the restriction in the cross-section. At the same time, due to the laws of fluid mechanics, the static pressure at this point decreases. Consequently, different values are detected in the pressure chambers of the sensor, a higher pressure before and a lower pressure after the orifice plate. This pressure difference is a direct measure for the flow velocity, and thus the mass and volume flow in the pipe. The higher the flow velocity and the resulting drop in pressure around the orifice plate, the greater the differential pressure measured. In numerous industrial applications, the orifice plate covers many needs of flow measurement technology. However, other designs are available for certain measuring tasks to minimize undesired effects, such as excessive pressure loss or abrasion of components due to solvents carried in the fluid. This demonstration shows that an abrupt restriction generates severe turbulence in a fluid. Nozzles with a rounded, funnel-like inlet clearly reduce turbulence and thus create less pressure loss. Nozzles are particularly suitable to higher flow velocities or to fluids with abrasive solid particles. Turbulence reduction is even greater with Venturi nozzles. And finally, with Venturi tubes, where the restriction is created by longer conical constrictions in the pipe wall. All these designs can be supplied with different restriction diameter sizes, so that the pressure loss and the differential pressure generated can be optimized for the process conditions. Industrial flow measurement using differential pressure has been tried and tested in numerous applications worldwide for about 100 years. With this measuring principle, all liquids, gases, or steam can be measured, even at extremely high process pressures and temperatures. Every differential pressure flow meter manufactured by Andrus and Hauser is configured to customer specifications and pre-mounted.
Andrus and Hauser is cheaper than the Micromotion, okay? They have Coriolis flow meter too. So now you know about pressure drop method, differential pressure. So we have number one, Isaac, what is the pressure drop method? Which method that use pressure drop to calculate flow rate?
Differential pressure flow meter.
What are those? Number one that you just watched is what? Something that have the name plate,
The orifice.
orifice plate. What else that you get from the video? There's orifice plate and what else?
We got another one called the Peter tube.
No, we didn't watch Peter Tube yet. So we have orifice plate and what?
The Venturi.
Venturi, okay, yeah, Venturi. What else? We have three of them. Nozzle, right? So you have nozzle, Venturi, and orifice plate. So you need to know at least one to do the exam, okay? So this one is a P-dot tube, working mechanism of P-dot tube.
Daniel Bernoulli discovers a direct relationship between the pressure and speed of a fluid flowing in a pipe. At the same time, the French engineer Henri de Pitot is constructing a device for measuring the traveling speed of ships using flow pressure. His instrument is known as the Pitot tube. Here is how this measurement method works. Pitot tubes have a rod-shaped measuring element that is inserted into the pipeline perpendicular to the flow direction. On the front and rear of this probe are several holes. 2 separate tubes connect these holes to a differential pressure sensor. With its 2 pressure chambers, separated by a diaphragm, the tiniest pressure differences in the flowing fluid can be precisely measured. The individual pressure taps are distributed along the entire pipe cross-section to ensure a representative measurement. If there is strong interference in the flow profiles, it's advisable to fit a second pitot tube, rotated by 90 degrees. If the fluid is not flowing, the pressure before and after the probe is essentially the same. As soon as the fluid starts to flow, an additional impact pressure against the front of the probe is generated, also known as the dynamic pressure. On the rear of the probe, in contrast, only the static pressure, which is not related to the flow, is still measured. As a result, different values are detected in the pressure chambers of the sensor. Higher pressure against the flow and constant pressure on the rear of the pitot tube. This pressure difference is a direct measure for the flow velocity and thus the mass and volume flow in the pipe. The higher the flow velocity and therefore the dynamic pressure, the greater the differential pressure measured. Pitot tubes are able to register the flow in both flow directions. This means that balancing measurements, for example in gas pipeline networks, can be carried out at any time. Continuous improvements have been made to pitot tubes over the past decades. Devices with a built-in temperature sensor, for example, together with a flow computer, can also calculate temperature-dependent mass and...
Corner, are you typing something? For the lecture, right? Of course. Okay, you see pitot tube, right? The problem with the differential pressure type flow meter is that it needs to be... It works for some fluid, but may not work for another fluid. You need to calibrate it, okay? Because the pressure drop per unit length change if your viscosity change, right? Let's say you have orifice plate. If you have that for, most of the time you use that for gas, right? But if you use for water, it will be different. Water not good for orifice plate. So those things quite sensitive to the type of the fluid. If you just flow natural gas all the time, it works. Okay. The Coriolis flow meter, it works for both gas and liquid. Okay. But the orifice plate just for gas. That's most of the time that they use. Okay, vortex, this one used for gas too. So vortex have it creates a pressure drop and the flow becomes turbulent flow and it generates a vortex.
Inside each vortex flow meter, a bluff body is located in the middle of the pipe. This body is a kind of obstruction that disturbs the flow. Downstream from the bluff body is a mechanical sensor which can register the tiniest pressure differences in the flowing fluid. If the fluid is not flowing, no vortices form. As soon as the fluid starts to move and reaches a certain flow rate, vortices gradually appear downstream of the bluff body. These vortices are detached alternately on either side of the bluff body and are carried away by the flowing fluid. Zones of high or low pressure now appear downstream and thus create a phenomenon that is known as the Kármán vortex street. These differences in pressure exactly match the frequency of the passing vortices and are precisely registered by the mechanical sensor, shown here in slow motion. This sensor is unique because it's inherently so well balanced that pipe-borne vibrations of up to 1 G, pressure surges, and temperature shocks have no effect whatsoever on the measurement.
So this measurement is to use to count the vortex frequency, right? How many vortex do you have per time? And that can be back calculated for the flow rate, okay? So whenever you have a flow meter, it causes some pressure drop, okay? So if you want less pressure drop, you have to use a bigger flow meter or change the type of flow meter. There's some type of flow meter that cause no pressure drop, okay? If you have a pressure DP flow meter, is based on differential pressure, right? You need pressure drop to calculate flow rate. There's another type, ultrasonic. It's not about pressure drop or anything. So when we have a, we use ultrasonic to get the
Nobel Prize winner Lord Rayleigh. His book on the theory of sound, published in 1877, describes the propagation of sound waves in solids and gases. Here is how this measurement method works. Inside the ultrasonic flow meter, pairs of sensors are fitted across from each other in the measuring tube. Each sensor can alternately transmit and receive an ultrasonic signal. Simultaneously, the transit times of these signals are measured. The ultrasonic signals are generated with piezoelectric crystals applying a voltage. Conversely, a piezoelectric crystal creates a voltage when an ultrasonic signal impacts the sensor. By increasing the number of sensor pairs, it's possible to accurately detect and mathematically compensate for flow profile distortions over the entire pipe cross-section. When there is no flow, the signal transit times are the same, upstream and downstream. Once the fluid starts to flow in the measuring tube, the ultrasonic signals are accelerated in the direction of the flow and decelerated against the flow. As a result, the ultrasonic signals now have different transit times, less time in the direction of flow and more time against the flow. Therefore, the differential transit time measured by the sensors is directly proportional to the flow velocity in the pipe. Together with the known tube cross-section, the actual flow volume can then be calculated. The greater the flow velocity, the greater the measured time difference between the two ultrasonic signals. For ultrasonic flow measurement, the sensors do not necessarily have to be fitted into the pipe wall. With a clamp-on system, for example, the sensors are fastened directly onto the outside of the pipe. They can be retrofitted at any time without interrupting the process. With clamp-on sensors, the ultrasonic signal is passed directly through the pipe wall and into the fluid. The signal continues through the fluid, is reflected on the opposite pipe wall, and then measured by the second sensor. In this example, with a two-traverse installation. The clamp-on design is unique because flow rates can be measured in very large pipes, up to 4 meters in diameter. This possibility increases the areas of application, for example, in the water and hydroelectric industries.
Okay, so this one example of flow without pressure drop, and then measure the gas. Are you awake? Are you awake? Good. Okay. So the to left, you want to watch this positive displacement thing.
Progress and isolate a volume fluid.
So this is look like a gear pump, liquid flow around it, and we count how many volume that we move from bottom to top. Okay, electromagnetic field. This one has a. Okay, let's watch this. This one is kind of unique.
Magnetic flow meter. Let's take a closer look at how this measurement method works. 2 field coils are located inside each electromagnetic flow meter. With the help of what are termed pole shoes, these coils generate a constant magnetic field over the entire cross-section of the measuring tube. To Two electrodes which can pick up electrical voltages are installed at a right angle in the wall of the tube. The lining fitted on the inside wall prevents electrical short circuits between the conductive liquid and the metallic tube. If there is no liquid flow, no induced electrical voltage is measured at first between the two electrodes. The electrically charged particles of the conductive liquid are evenly distributed, shown here in water with red and blue particles. However, as soon as the liquid starts to flow in the measuring tube, the magnetic field applies a force to the charged particles. As a result, the positively and negatively charged particles in the liquid are separated and collect on the opposite sides of the tube wall. Now an electrical voltage forms, which is detected and measured by the two electrodes. This voltage is directly proportional to the flow velocity in the pipeline. Together with the known tube cross-section, the flow volume can then be calculated.
Okay, good. We don't use this for that oil. So most of the time you use either for oil flow, you use the positive displacement type, the kind of sliding vane, the vane meter, and Coriolis. That's for liquid. For gas, you use either Coriolis flow meter or Orifit plate with the Daniel senior fitting. Okay? You're awake. So now you should be able to tell me different kind of flow meter that is available and which one do we use. Okay? And very important is working principle for Coriolis flow meter. If you don't really catch that, go back and watch it again on how Coriolis flow meter work. Okay? And you will be ready for next week quiz. Don't you think? Okay. Alright. We still have 12 minutes, okay? So the link on the video already there. So if you want to rewatch or you just do your homework during the time that I play the video, you can go back and rewatch it and do quiz next week. So selection of the meter. The flow meter is expensive, okay? Flow meter can be the most expensive part of the facility sometimes, okay, depending on how big. In the field, you have a big equipment, so flow meter may or may not be the most expensive part. But like in the research facility, for example, in my lab 101, the most expensive part is flow meter. It's $13,000, just that. Okay, so flow meter is very expensive. This means we need to know how much accurate do we need. To be able to size a flow meter, you need to know what type of fluid. So when you contact your Chris, who sits next to you, what's his name?
Brandon.
Brandon.
Yes, sir.
Okay. Are you okay?
I'm good.
Oh, you're good? Okay. So when we want to size a flow meter, you typically don't know what kind of model number you need. So let's say you want to size a Coriolis flow meter. What you do is you can open the manual from the internet, from Emerson by yourself. But it would be better if you can tell them what is the flow rate range. So they need to know how many kilogram per hour that you try to measure. Of course, you don't know that number, but you know the range, right? You can tell, okay, maybe it's between 1,000 to 10,000 or something, or maybe between 500 to 20,000. Okay, so if you have low flow rate, you want to use smaller flow meter. If you have big flow rate, you want a bigger flow meter. So you may switch between those two. For the case of research, okay, not in the field. For the case of research, you may have two Coriolis flow meter, small one and big one. So when you want to do high flow rate test, you use the big one. when you use a low flow rate test, you use that one. That is not for the, not in the field. In the field, you have the lag unit. Your lag unit has either the PD type or the Coriolis flow meter, right? Just that thing. Oh, when you install the flow meter, you should install it for gas flow. You should install it like this. Okay, this will be good for gas flow. If you cannot install it vertically, you can do like this. Okay, so if there is any liquid accumulation, it will not stay. So it will come out and stay over here. Right? If you install it vertically, if you have any liquid condensed, it will drop. It will drop out. It won't stay here. Okay. But if you install it like this, liquid will accumulate on the bottom. Not good. The accuracy of the measurement is not about the direction that we install. So the direction that we install is just to prevent any accumulation of liquid. When you size a flow meter, you tell the manufacturer about the type of liquid. Whether you have H2S or you don't have H2S. Whether you have low viscosity oil, high viscosity oil. Okay. Most of the time, you don't really specify the type of the meter. You just buy a lag unit and it's done, right? Just buy a lag unit, it's done. So if you do something that is not conventional, like for example, you go to subsea, you have subsea production, big platform. By the way, subsea production, there are still some construction over there, okay? Because they invest a lot of money already before the price drop. So even though the price drop a lot from 120 to 40, 50, 30, the project still continue, okay? It costs a lot, it just cannot stop. So the criteria to select the flow meter, we need to know the accuracy that we want, okay? Range, maintenance requirement, power availability. You need to know whether it's gas or liquid, cost of the part, susceptibility to theft or vandalism. Okay, so that one is actually important. So if you put Coriolis flow meter, very expensive, on your list, you need to make sure that it will not be stolen. Okay, I have copper wire be stolen from North Campus. They just come and cut the wire, cut the copper and sell it. The cost of the wire is a lot less than the cost of the installation. Okay, a little bit before we go, look at this one. Positive displacement gas meter. So the way it works is you have kind of piston, suck or take liquid in, or take gas in and push everything out. So take in and out is work like compressor, except it doesn't compress. It just count, do the counting, okay? Smith meter in the lag unit, AO Smith meter. So this is just a positive displacement type, like just push a known value forward. It don't really push, it's kind of counting how much do we push forward. Diaphragm gas meter, when you have your gas and you use natural gas, this is a diaphragm. So diaphragm is a positive displacement type. Okay, there's gas coming in, the diaphragm expand, the valve close, and it keep expand and close. Okay, so there's a valve. So this type is kind of positive displacement. This is just for low flow rate, right? For the residential case. So next part, a little bit on the calculation. Okay, we have more calculation. Volumetric pressure. You by now should be familiar with this equation. Simplest method for measuring gas by volume method. Q equal to V multiplied by PT over PV, PTZ. So basically it comes from PV equal to nRT, right? And you select your base pressure. By now, you probably know already that base pressure does not need to be 14.7. it can be 15.0 to 5 if you are in Mississippi. Okay? So depending on the location or the gas contract that you need to report. Volume of the piston for the rod. So this just to count how many registration we have. And this is application specific. So this equation is the one that you need to know. Okay? Just that. That's one not that important compared to 6.2. Volumetric measurement, standard cubic foot per day. You see everything starts with PV equal to CNRT. Then we have the ratio PQ over PV equal to TV with T. You will review this by yourself and it will pop up in the exam. Okay, very easy for me to make you learn, I hope. Okay, differential pressure, pressure flow meter or refit plate is the most common. That's a meter I have seen on the field today. There's not many. Some still has the paper and the chart to read. Many of them is just digital. Okay, this is the senior orifice fitting to take the plate out, put it back in. Okay. All right. This one, pressure distribution in the orifice plate. Look at this carefully. This one actually in the exam last year. You see this? P1, highest pressure is P1. Lowest pressure is not P3, but it is actually P2. So this is a flow profile, and we have circulation zone. So the pressure, you have a little bit of pressure gain when you move from here to there. Okay? When you go across the orifice plate, you have pressure drop. Okay? This point is the point of minimum pressure. And there's a name for that. That name is on the exam, of course. Okay? It was on last day exam, and you should know that. It's called vena contracta. Just memorize it the day before the exam. You will be fine. Okay? My point is, the lowest pressure point is not this point. Is the point that you have vena contracta, the most condensed streamline. Okay? And that's where you have pressure measurement. Alright? When you have an orifice plate, the flow needs to be uniform. So most of the time you have flow conditioning. It's just a plate that have hole in it. So you have a smooth streamline. I have about 20 seconds left. I hope you still sit here. So next week we have, when do we have a lab? This week we're gonna have lab. I don't know about next week. I will tell you again on Tuesday we have the lab. If we have the lab, it will be about fluid flow. I expect the homework on tomorrow. Okay, tomorrow we shall have homework, and it will due on not next Friday, but should be Monday after next Friday. And if you want to meet me about the homework, please, especially Sebastian. Okay, thank you for coming. See you next time.